Every time you check the phone in your pocket for directions, you are relying on a direct application of Albert Einstein's theories of spacetime. Since early consumer devices brought this technology to the public, we've taken for granted the ability to know our absolute position on Earth at any given moment. But if you ask how this system calculates that position, the most common answer you'll hear is triangulation. That is false. The global positioning system does not use triangulation, and it never measures angles. The system actually uses a geometric principle called trilateration. Instead of measuring angles, a GPS receiver calculates its position exclusively by measuring distance, and it finds that distance by measuring the exact time it takes for a radio signal to reach it. Finding your location on a map isn't a geometry problem about intersecting lines. It is a precise timing problem, bound by the speed of light. GPS satellites constantly broadcast a data packet known as a pseudo-range. This signal contains two critical pieces of information: the satellite's exact position in orbit and the precise timestamp of when that signal left the transmitter. A received signal places you on the surface of a massive sphere. A second satellite creates another sphere, their intersection forming a circle. A third satellite intersects that circle, reducing your location to exactly two distinct points. Because of orbital geometry, one of these points will always be thousands of miles out in space, or deep inside the Earth's crust. Your receiver simply discards it as an impossibility. Mathematically, three satellites provide a complete three-dimensional position, but this entirely relies on a massive assumption that the clock inside your receiver is perfectly synchronized with the clocks in orbit. To calculate the distance to those satellites, the receiver relies on a basic equation. Distance equals rate multiplied by time. The rate is constant. The radio signals travel at exactly the speed of light, roughly 300 million meters per second. Because light moves so incredibly fast, a tiny error in time translates to a massive error in distance. To achieve a standard navigational accuracy of 5 meters, the signal's time of flight must be calculated to within 17 nanoseconds, 17 billionths of a second. To generate departure timestamps with that level of extreme precision, each GPS satellite carries multiple space-qualified atomic clocks. Navigating the world is no longer constrained by our ability to measure angles or draw maps. It is entirely bottlenecked by humanity's ability to measure billions of a second. Here lies the practical hardware problem. Your phone does not have an atomic clock. It relies on a standard, inexpensive quartz oscillator, which constantly drifts. Because your local clock is slightly out of sync with the satellites, the time of flight calculation is flawed. That single intersection point blurs into a large, fuzzy zone of uncertainty, rendering the location useless. This is why a receiver requires a signal from a fourth satellite. It provides a fourth intersecting sphere, which collapses the fuzzy zone back into a razor-sharp position. The fourth satellite isn't just providing an extra spatial coordinate. It provides the final algebraic variable needed for the receiver to solve for its own internal time error, known as the clock bias. This four-satellite trilateration perfectly syncs a cheap local receiver to Earth-centered, Earth-fixed coordinate time. But maintaining that perfect synchronization immediately runs into the rigid limits of spacetime. The atomic clocks in orbit and your receiver on the ground exist in radically different relativistic reference frames. The first force acting on the system is special relativity, which dictates that clocks moving at high speeds tick slower than stationary ones. GPS satellites orbit at a velocity of roughly 3,874 meters per second. Because of this speed, their clocks experience time dilation, dragging behind clocks on the ground and losing exactly 7 microseconds a day. The second force is general relativity. Gravity affects the passage of time, and clocks closer to a massive object tick slower. The satellites orbit at an altitude of over 20,000 kilometers. Sitting high up in this much weaker gravitational potential means the orbital clocks run faster than ground clocks, gaining 45 microseconds a day. Combine the two, and the satellites experience a net drift of 38 microseconds every single day. Remember, a 17 nanosecond error puts you 5 meters off course. A 38 microsecond drift equates to a navigational error of 10 kilometers per day. These relativistic shifts function as a macroscopic mechanical force. Without compensation, the GPS grid loses all utility in under 2 minutes. So how do you maintain a globally synchronized grid without forcing every mobile phone to continuously process complex Schwarzschild metric tensor equations? You build the solution directly into the hardware before the satellite ever leaves the ground. It's a pre-launch calibration known as the factory offset. Engineers deliberately down-tune the fundamental L-band frequency of the satellite's atomic clock. Instead of taking at the standard 10.23 MHz, it is set to exactly 10.2299999543 MHz. While the satellite sits in a clean room on Earth, its internal clock is intentionally programmed to be wrong. It runs slow. But as the satellite launches from Earth and stabilizes into its high-altitude orbit, the physical environment around it radically changes. The combined forces of relativistic time dilation and gravitational shifts act on the hardware, naturally speeding the clock up. Once on station, it ticks at exactly 10.23 MHz, perfectly synchronizing orbital proper time with Earth coordinate time. That hardware offset is an elegant solution, but it only accounts for the constant relativistic effects of a perfectly circular orbit. In reality, satellite orbits are slightly elliptical. As a satellite moves closer to Earth, its velocity increases and gravity strengthens. As it moves further away, velocity drops and gravity weakens. The relativistic effects fluctuate continuously. To fix this, your receiver's microcomputer calculates a dynamic, periodic algorithm in real time, adjusting for the precise orbital eccentricity of every satellite it tracks. True navigational accuracy demands a symphony of solutions: rigid pre-launch hardware offsets, combined with continuous algorithmic software corrections. Without these precise corrections, the coordinate grid overlaying our world would instantly warp and drift out of alignment. Instead, we experience perfect, engineered stability. If that stability failed, global logistics networks, aviation routing, and daily navigation would simply cease to exist. The constellation functions as a global utility, maintaining this synchronization across the entire Earth's surface 24 hours a day. And it stands as one of the only technologies in the history of human engineering where the abstract tensor calculus of general relativity is an absolute, unavoidable requirement for daily operation. Every single location update on your device serves as a real-time mathematical proof for the curvature of space-time.